So, as I told you, I'm actually a compiler guy. But the next talk is about DartVM from a front-end developer, because I was a freaking front-end developer previous talk. So, no, I'm still a compiler engineer after all. This will be a very quick talk because I don't really, I did not draw any nice pictures and I don't have any like hello Oslo things to say about DartVM, where stuff is bound and whatnot. I'll just tell you what we think, why the Dart was designed in some places the way it was designed, and because we really want to achieve better native performance as well. So we don't only run Dart via compilation to JavaScript like Florian was telling to you, but we also have a native VM which we use, and which, for example, powers Dartium. I present actually from Dartium. It powers Dart.io, so you can have the Dart running on the server side with the Node-like APIs. Well, not exactly Node-like, but also asynchronous. So Node uses callbacks, and we use futures and streams. Node also use streams, but they're a little bit different. So, okay, doesn't matter. So we want a good performance on the virtual machine. How do we achieve that, and how we designed the language to achieve that, I'm going to talk to you now about. I'm like Yoda now. Okay. So, when I'm talking about the performance of virtual machines, I always say that there are 3 things you need to solve when you build your virtual machine, when you build your own language. So, these 3 things coincidentally all start with R, like the pirate virtual machine. I don't know. R. So, representation is the way you represent your objects efficiently, and by efficiently I mean that you have to like use less memory, and at the same time you want to have a quick access to whatever your objects contain. The resolution problem is that you want, if your object contains something or your value contains something, you want to quickly get it out. You want to understand where this something is stored, in which format, and pull it out quickly. And the redundancy is that, like, if you executed some action twice in a row or close to each other or so on, how do you maybe eliminate the second execution and you keep on the first one? So this is the 3 biggest problems you have to solve when you design your virtual machine. And also you have, when you design the language, you have to plan for all these 3 problems. How are you going to address them in your virtual machine that you will later build for your language? JavaScript, it has no R in it has all R, but not all 3 of them. So basically, it was not completely well thought in that direction. Neither is Dart, kind of. But it's better. So let's talk a little bit about JavaScript. So some people say that this is the most best way to create your object in JavaScript, because Douglas Crockford told them so, I think. And some people actually construct objects like that. I just use it for illustration. So here, when you look at this code as a virtual machine, and virtual machines, they're pieces of C++ code. They don't have brain. They have a lot of questions in this place they have instead of brain. And these questions, they look like this, size of P. So I want to create a P there. How much memory do I have to reserve for it? Like when I call object.create. I don't know nothing about like px and py maybe that come later, and maybe there is pz somewhere here, not on my slides, assigned to this object. How do I allocate just enough memory so that everything fits, but also I don't waste memory? Kind of like that. Where px goes, like when I arrive to the place where I have to store px, how do I find the place where I put it? And if I want to load it, how do I find the place where this px previously went? What is this p.len? Like, it sits somewhere on the prototype. How do I quickly traverse the prototype chain and find this len, and maybe I can avoid traversing the prototype chain? Again, questions, no answers. Let's look at this array here. Maybe for people who are sitting very far away, they don't even see that, but there is this double comma there. This double comma says, there is a hole in this array. I'm a hole, hello. So if you write something like that, array prototype 4 equals hello from the whole, and then you load from the 4, you get what? Hello from the whole. So yeah. And in reality, so it's called array, and it kind of behaves like array. But it's not really array in the sense that, for example, languages like C or Java or many other normal languages perceive arrays. It's just an object with properties called 1, 2, 3, so on, also property lengths. And all of them are strings because in JavaScript there is no numerically named properties. The properties are always called by strings. So if you ask the property with a string 1, you get the first element from the array, or the second, yeah, because arrays are from 0. I'm a little bit already going crazy. So yeah, you get this second element. Okay, it's again a problem because you really want in the memory, you don't want to store this array with 1 billion elements like a hash table with the properties called 1 and so on, or 0 and so on. And you want to have a nice tight memory layout, 1 billion multiplied by 4 bytes. Yes, so anyways. Another question here is, like, if I have the array that contains only doubles, can I store it more efficiently than array where each element is pointing on a box which contains double? Because so we are dynamically typed, so the doubles, they need to carry some tag, kind of, which tells that this object is a double. They cannot just, well, there is a trick to store them directly, but the question is, how do you pull these tricks out? Like, how do you make the array which would be as efficient as the C array of doubles, so like float 64 array, which is the closest thing you have in JavaScript for the C's arrays of doubles? More questions. Like, if I have this normal JavaScript array and then I take element with a number, number 6, yeah. So you take the 7th element of the array, which is not here, because this is the 5th element, and there is a 6th element here. And actually, this is not a double array, this is an array of integers. Did you notice it? I did not notice when I was making slides. I was too sleep deprived. So I want to make it an array of doubles. Just to, yes. So in JavaScript, there are no distinction between double and integers. There is only double. So actually, VMs are clever enough if you have only integers. It doesn't matter that you write it 2.0. I programmed Dart for too long. If you write 2.0, you can still be represented as an integer. Anyways, we will return to that later. So here, the 6th element is not there. So it goes to the prototype. If nothing is on the prototype, you get undefined back. Undefined gets coerced to the 9 in the arithmetic, and then now the 6th element contains nan. So how do you do that efficiently again? So yeah, here are the problems of JavaScript that we tried to kind of remove in Dart. So properties don't come and go. They just sit on their chairs and don't go anywhere, stay there. Then there are, like in JavaScript, there are no methods. It's just properties containing functions. We want to have real methods. And there are no early errors in JavaScript, like you can coerce all kinds of strange things to all kinds of other strange things. And there are no errors, and it keeps on tracking. As Florian said, I don't really know what it means. Okay, so, and the problem that VM tries to solve is that because these things, they just, in constant fluctuation, you can see nothing is defined. And the VM has to solve the problem is it has to find this efficient representation while the program runs. So there is no this step when you load the site and then it says, oh, wait a second. I need to think what's the most efficient representation for this code is. And then 10 minutes later, it's like Eclipse pops into your face and you have this nice page with 2 buttons. Yeah, so it has to do it quickly and it has to do it while the program runs, or while the site essentially runs. So the way the JavaScript VMs solve it is to use hidden classes and transitions. And I told the story of what it is so many times that I don't really want to tell you today. What you should kind of have in your head is an idea that VM tries to track how you use your object and what you add to it and what you remove from it. And it tries to create on the site a structure that tells like this is kind of a class of this thing, if you could create a dynamic class. Okay, I'll try to illustrate it a little bit. So let's try to illustrate. So it's very powerful, very complex technique. I can't even explain what it does. And it contains a lot of heuristical approaches. So, okay, let's look how it actually. So remember the point. I was talking about point. So what VM can figure out at some point of your program, once you edit all the properties to it, is that it has this structure on the side which tells that there is a property X which comes first, and then there is a property Y which comes second, and then there is a prototype which has the len property which contains a function. So it just tracks whatever you edit there and in which order, and then it creates the structures on the side. And these structures are all interlinked together. So for example, when you just edit X and there was still no Y, then there would be no Y here. But then you add Y, it just creates a new one and connects the old one which contained only X with a connection. So that's called transition. Anyways, doesn't matter. So you can understand the end result, that there is a class this here that tells what's inside the object. And for double array, for example, it can figure out that it contains only doubles, now that I fixed the previous slides, and it has a holes. It can also track whether there are holes, and maybe there are no holes, then it will say no holes, and only doubles. And the most important property of the hidden classes is that the same hidden class means the same structure. So you can notice I'm in the middle of the presentation, and I'm still talking about what JavaScript VMs do to just solve all these kinds of problems that JavaScript brings to them. Nothing of this is really needed in Dart. So yeah. Hidden classes enable inline caching for JavaScript. So when V8 just came out, you all remember V8, maybe, I don't know. Who remembers V8? Cool, okay. At least somebody still remembers V8. The only thing that it had no optimizing compiler. It just had a thing called inline caching, which was developed in, got forgotten, 80s, when everybody was hip enough. I don't know. So for self and small talk. And this technique essentially allowed V8 to speed up JavaScript execution considerably because nobody else was using it on the scale that V8 was using it. So inline caching is very fundamental optimization. I will quickly mention it because Dart actually uses it. It doesn't use the hidden classes, but it uses inline caches. So the idea is very simple. So if we see this p.x, there is no way we can ahead of time usually answer the question where this x comes from, as I told you, because everything comes and goes and so on. But once we did arrive here once, we can observe what kind of hidden class was there of the p, and where that hidden class had x, and then we just remember. And the next time we come there, we say, is it the same hidden class? Then we already know where x is. So it's just a simple table, which maps the hidden classes to the places where the lookup results or something else is. So it's just like normal cache, key value store. So for example, here it can look like that, like it has seen some hidden class, and then, oh, the x was at the first property in the object, that's it. So if you see again this class, just hit here and load it, and that's it. No need to perform the complicated lookup procedure. So the JavaScript lookup procedure is very complicated because it has getters, setters, prototypes. It also, because in the browser it runs, there are interceptors and more stuff. But here the answer is like, it's a simple property loaded from the offset, done. The binary operations, you can apply, that's not necessarily limited to the property accesses. Like the binary operations, they use this all implicit conversions between different representations of integers. They can different conversions between undefined null numbers, whatever. You can remember what you saw on both sides and what was the result. Like I saw double and double and I returned double. Or I saw small integer, and then multiplied, and I overflowed into 32-bit integer range. So it can remember that. And all of that is like observed, and you can use it to first speed up the execution with inline caches, but then you can take it to the next level and feed this information to the optimizing compiler. We will talk a little bit about later, now that we proceed to Dart. So that was all 28 slides of complicated stuff that JavaScript VMs do, and I did not even scratch the surface of the stuff that you have to do to get it run at the speed we got to run in now. Dart is much simpler. It has fixed class objects. So once your object got a certain class, never changes. The classes themselves never change either. They have real methods. You cannot monkey patch, so on and so forth. It has real arrays. And you have real arrays with a fixed length as well. So if you have some array and you know it's a fixed length array, you know the length will never change. In JavaScript, you can seal, you can override the properties, the properties of the attributes of the properties, but then good luck. No modern VM actually runs this code fast, I think. So yeah, and Dart has real arrays with a fixed length as well. So it has the separation between numeric types. So you have integers of arbitrary precision, like whatever you do with integers, like multiply, divide, subtract, never overflow. They overflow into like big integers, and so on, like in Python, for example. It has doubles, which are double precision arithmetic, with a little bit usability improvement that if you multiply int with double, you get a double out. So you don't get an exception. I would really like to have an exception. But no, unfortunately not. So, and also it has SIMD types, so you can have on the platforms that you have single instruction multiple data primitives, like all modern CPUs, like Intel or even ARM. Well, even that was very offensive, so yeah. Or ARM, you can write this code which operates on vectorized values with one instruction, like to multiply 4 elements and so on, which is very useful for games, physics, and so on. And they're all separated. So when you use like inline caching, you can see there. You don't have to perform the range inferencing like you do in JavaScript. In JavaScript, because you have only double type, you don't want to store all the values in double because it's just too much space and so on. You want to store some integers as integers, and then you want to overflow into double. So you do range profiling to understand when the integers can be used. But in Dart, you just use the type to understand when the integers are used. Okay. And it also has early errors and the lack of coercions, which is predictable for both programmer and virtual machine, in the sense that usually, like, you don't have some undefined sneak into your code and slow it down because the multiplication of undefined with nan is not handled on the fast path. I am not telling you it as a joke. I am telling you it as a practical, real thing. One of the benchmarks I saw was measuring how fast you can multiply undefined with nan. And because there was a typo that sneaked in, and then people published benchmark, and then we looked and we said, approximately this. Yeah. So it's predictable for both virtual machine and the programmer, which is good. So you get the predictable performance out. But the data is still dynamically typed. As you heard, annotations mean nothing. So you still have to use inline caching to speed up the resolution of the properties and so on. But once you have all inline caches populated, so we use the inline caches that are very simple. So V8 uses very sophisticated system of the inline cache stubs, where you have pieces of code generated and patched into the other pieces of code to provide the peak performance for inline caches. Each inline, because V8 came out when it used nothing but inline caching, so it had to provide the peak performance from each inline cache. But for Dart, we already knew that we are going to implement the optimizing compiler, which V8 got much later in its lifetime. So we just use the simple polymorphic inline caches, which are maps, as I described before, from class to the lookup result, not V8's stubs. Okay. So, oh wow, I have even duplicated slides. I did not really get enough sleep, I guess. So, anyways. And we have a compilation pipeline which has non-optimizing compiler and the optimizing compiler. So I have this picture drawn at some point in the past. So that's how the compiler looks for a 2-year-old kid. So you start with the source, you build the abstract syntax tree from it, then you generate intermediate representation. So IR means intermediate representation, or yeah, or something, or internal representation. So, and then you have 2 passes. So first pass is just a simple line here that goes and reaches backend, which just emits native code. It's a very non-optimizing compiler, is this line. And this compilated code, the native code will compile. Right? I'm really compiled code. Non-optimized compiled code contains a lot of inline caches. And then you run it for some time, and then it becomes very hot. And when it becomes very hot, you want to compile the same source again, but this time use this complicated spiral of optimizations here. So, and to fit these optimizations, like you need to know something about types. The compilers that operate ahead of time, like Dart2.js, they can use global analysis. But we cannot allow ourselves to use global analysis because it's too time-consuming. So instead, we just feed this observed information from inline caches into optimizations, and then we guard the assumptions that we make based on the information from the inline caches. And here you see what kind of types are used in this code, and then you just check that the types you get in this code are the same, and then you use only specialized code paths. Okay, and then you feed again into backend, and then you get native code with less ICs, ideally with no ICs at all. So, and if some assumptions are violated, then you just jump into the unoptimized copy of the code. This process is called the optimization. So it's a fairly classical approach. Oh, wow, I need to refresh this. Yes. So this is a list of optimizations that we do. I'm not going to go into details about them. They're very classical. V8 does some of them, does not do another ones. But the thing about Dart is that many optimizations are either simplified or just enabled for us by the simplified semantics. In V8, you cannot do this, for example. If you have some call, and then you checked that a certain value has a certain hidden class, then you cannot here assume that it has the same hidden class, because in that call you can just access this value, and then that's it. You can delete properties, add properties, so on and so forth. You cannot simply assume. In Dart you can, because the classes are frozen. So here you do check, you call, and then you do not have to check again at all places that are dominated by this check. So this is one of the things that simplified semantics enables us to do. And I will just, the rest I will quickly glance over one of the optimization that I really like, which is called load forwarding and allocation syncing. And let's take a look at this example. This is a Dart code. This is how you can write an iteration over the list. This code gets desugared to something like that. You ask the iterator from the list. Oh, I spelled it incorrectly. It should say it, but it's fine. So you get the iterator, you move it, and then while it moves, you get the current element and then use it somehow. Yeah, obvious. So now let's start inlining all this stuff. We apply inlining first, and first we inline the getter. So this getter is just creation of the list iterator with a list. Then you inline all the other methods, and then you have an allocation of a list iterator, then you assign 2 fields. I'm simplifying some things, but okay. Then you just, this is index field of the iterator, you just move it forward, and then that's how the move next looks like. While it's still less than length, you get the current. This was the current getter. One thing to notice here is that here you stored the list, and here you loaded this field. And nothing in between interferes. And nothing can actually interfere because nobody else is using this iter, because it doesn't escape anywhere. It's just a variable that was used in this desugaring, and it's not used by any other code. So it's a local object. Nothing can interfere with this store. So we can just forward this value that was stored to all the loads. And you do that, and then the load disappears. So this is called store to load forwarding. And then you just continue. You observe that this IDX, you can perform similar operation, except that there are stores here. But what you can do is that you can introduce kind of the fake variable. That's not what VM actually does. I'm just explaining it on the source level. A fake variable, a fake local variable, that is just always in sync with the value of the field. And you move the variable and then you store it into the field, but you use only the variable itself. That's it. now we can also use the loop invariant code motion to, there was this list.length. You can move it out. It actually will be moved out earlier. Doesn't matter. So now we have this all the tight code, but there are still these stores into this iterator which nobody uses. So that's the only uses of the iterator. Like we allocated it, we initialize this field, and this field nobody loads from it, but we still store it. So now we just sync the allocation, eliminate it at all, because nobody can access this object, nobody can observe it, which means if we remove it, nothing will change. Like if we just remove all this code, nothing will change. And that's what VM does, and you end up with the code like that, which looks like what you would write if you write for I equals so on. This optimization is beautiful because it's not limited to the iterators. It's not like VM says, oh, there is an iterator, let's just do that. No, it's a completely generic optimization that can be applied to all the temporary objects which do not escape, and sometimes even to those that can escape, but we did not implement that yet. If you have a vector, an immutable vector, which you can add, like here, you can add two vectors together. It's similar to the point that Florian was showing you first. And then you can do the dot product, the cross product of two vectors. And then you write the code like that, like you add two vectors, and then you add two vectors, and then you do a dot product, and the result is a scalar value. Actually, if you don't apply the allocation syncing and load forwarding, there will be one temporary object here, one temporary object here. But with this optimization, you have 0 temporary objects. You just take them values, mash them together, and you get the scalar value here. That's why this optimization is powerful and useful for all abstract code that produces a lot of temporary objects. So thank you. I guess that's it from me because I'm very precise, 7:30. Yeah. Yep. Any questions? Well, did I speak Russian all the I just remembered the story. Okay, I will tell you the story just to finish the. I was learning Danish, and somebody asked me to translate something from Danish to English, and I started translating, and people were looking at me with blank faces, and I thought I am mistranslating, so I started again and again, and somebody kidded me and said, "You're speaking Russian." So while everybody was expecting me to speak English, of course, when you ask to translate Danish to something else. Anyways, yeah, any questions? Not about the last story, but about that. I really want to get, well, maybe these ones are so nice I will take them with me, but yeah, I want to get rid of pins. Okay.
Is there some optimizations which is not possible to do in V8?
Yes, it's a good question. The V8 implements part of those optimizations, and they recently tried to implement the allocation, folding, and so on. It's just more limited, and you really, if you have a call inside this loop where you create this temporary object, it's very hard to determine what leaks out and what not, and it's just, like, it's more predictable that the optimization will hit your code in the Dart than in JavaScript, where you have to, like, as soon as you get some function not inlined by accident because the budget was exhausted or something, the optimization does not trigger, and then your code becomes slower, and then you have to go figure out. And with Dart, you just look at the code, and you can say this optimization will trigger, and that's it. So, yeah. Well, you have a pin, so I will return to you. But you can ask the question. Yeah, okay.
So what are the next optimizations that you're looking into? What kind of performance gains can we expect?
That's a good question because I have not worked on the VM for a while, and actually, what I was, oh yeah, so generalizing the allocation syncing to be even more powerful. Like there are certain cases which with like complicated objects, nested objects, which it doesn't hit, just because you need to better escape analysis and so on. Like generalizing that, and yeah, that's one that comes immediately to my mind. But there's still a lot of work there, obviously. So the work of the optimizing compiler engineer are never done. So there are optimizations that I can say for sure. That would be it. Yeah. Yeah. So right now we just do a mark sweep, and with so there is, it's similar to what V8 had back in the day before we rewrote it, and by we I mean me as well. There is a copying collector for the the young generation collections, and there is mark sweep for the full collections. There is no incrementality. There is no nothing in terms of like splitting this work. There is some ideas how to do the concurrent one. We really want to do a concurrent one, I think. Yeah, but right now it's just mark sweep with partial collections using the copying collector from the like two semi-spaces, like Chini copying collector. So, Yep. Does that answer your question? Do you want a pin? I hope I will not kill you. Can you pass the pin? Oh, sorry. No, you won't know. You can ask me privately. Yeah.
In general, the memory on the data object, how much smaller is it?
It is much smaller. So you have, in V8 objects, you have at least 3 words of overhead per object, not counting the inefficiencies of the allocation that can occur when you do not completely know, because you do not completely know the amount of properties you will store there. So you would save at least 3 words per object. But the Dart objects, you can see how big they are. They are precisely the amount of fields you have in them. And the V8 objects, V8 over-allocates objects to accommodate if you add the properties. So for the point, it's 3 words smaller. So it means 50% smaller. So that would be it. But it depends, again, you cannot answer this question in general. If your object is 100 fields, then the percentage just goes down. Yeah? Any other questions? I have 2 pins. I want 2 questions. Okay? It's very interesting. So there are obvious cases when we do not track really activities. Like, for example, we do track versus V8 on the benchmarks that we ported continuously, but versus Java VM we do not track. So it's hard to say. But on some benchmarks we are matching the speed. But it's, again, it should be very tight code, and the Java VM has its own challenges. Java VM is multi-threaded. Dart is a single-threaded language. So a lot of optimizations that I showed you, like even allocation syncing, becomes very hard because you can have the effects from other thread interfering. You need to accommodate for the memory model and so on. Dart VM is just much simpler because there is only 1 thread of execution. So, so on a tight object-oriented code, you can have cases when you are comparable speed to Java VM or faster. So, like on the Delta Blue, which we optimized for, it actually shows faster a little bit, I think, than the server compiler after warm-up. So, yeah. Okay? Yes? There is, so futures do not imply threading. So it's basically you schedule the task, it will not be executed until you return the control to the event loop. But at the same time, if you have some I/O, you can have the threads performing I/O, for example, on the in a thread pool, like in Node.js essentially, where you have the callbacks, and there is a thread pool that performs I/O operations, and then eventually it will post a message to the message loop that the callback has to be called. It's the same with futures. We also have isolates where you have no shared memory between instances of the virtual machine, but they all can execute in parallel, so that you can saturate the cores, for example. And there are plans to have transferable things between these isolates, so you can pass for socket descriptors and so on, and split the work. But the idea not to have shared memory, I think there will be never shared memory. So, okay, so still 2 pins. Oh, I did not get somebody. Did I give you? Oh no. Okay. Somehow I cannot throw. I am losing my power. Okay. Yes. Do you have a pin?
Yeah, so this is kind of a non-technical question, I guess, but I mean, you have the Dart VM working in Dart.
Yes.
Will it ever actually show up, at Chrome or anything like that?
Well, we hope. I mean, we wake up in the morning and we hope, and we go to sleep in the evening and we hope as well. So, yes, we hope it will happen, but I cannot say that it will happen. So. The Dart team lives for the day. It will continue to live after the day as well, but so it's not like we all will die, but yeah, we hope. So, do you want a pin? Oh, at least somebody almost caught what I threw. But anyways, yeah, thank you very much for your attention.